We have come to the end of Module 1. So let us list down some of the important takeaways from all the discussions. In summary, systems of linear equations can be solved using the Gaussian with back substitution method of elimination. Here, the system of equations is first written as an augmented matrix and a series of elementary row operations consisting of interchanging rows, adding multiples of a row to another row, and scalar multiplication are used to eliminate variables in succeeding rows until the row echelon form of the augmented matrix is achieved. From the row echelon form, the elementary operations can still continue in the backward phase until the augmented matrix is further reduced such that the leading one in a row will have zeros below and above it. This is called the process of Gauss-Jordan elimination. About matrices. Matrices are simply arrays consisting of rows and columns defined by size m by n, that is m being the number of rows and n the number of columns, and with entries a sub ij, that means an entry A is positioned at the ith row and jth column. Only matrices of the same size would have a defined sum. That means we cannot add two matrices that are of different size. A scalar will be able to increase or decrease a matrix entry in a scalar matrix. A matrix product is defined whenever the number of columns of A is the same as the number of rows of B. And matrix equality can be used to solve for problems involving matrices. About inverse of a matrix, the systems of linear equation can be expressed as a matrix equation AX equals B. Also, the matrix product AX can be expressed as the linear combination of the column vectors of A. System of linear equation can be solved using matrix inversion where X is equivalent to the inverse of A multiplied to B, where B is the column vector consisting of all the constant terms in the system of equation. To find the inverse of a matrix, the determinant method can be used as well as applying Gauss-Jordan elimination. That means applying elementary row operations. About determinants, a determinant of a matrix is a number associated to a matrix. It can be evaluated using the cofactor expansion method or the arrow method. The adjoint of a matrix is the transpose of the cofactor matrix, which can be used to find the inverse of a matrix. That is, the inverse of A is equivalent to 1 over the determinant of A times the adjoint of A. The system of linear equation can also be solved using Cramer's rule, which is an application of the concept of determinant. Also, we were able to apply the methods that we have learned in solving systems of linear equation in real-life problems. Real-life problems such as in polynomial curve fitting and network analysis are models of systems of linear equation. Examples of network are those in traffic, electric circuit, piping systems, among others. Also, you were able to perform matrix operations using Matlab. Matrices and matrix operation can be solved using the basic features in Matlab such as RREF of A, inverse of A, and the determinant of A, among others. So that's it for Module 1.